You know what's really cool is where a bunch of people came up in the break and asked even more questions that relate to just the concepts of power and alpha level and null hypothesis is true, ultimate hypothesis is true, and it kind of illustrates to me yet again that, I mean, we've all heard this stuff already, right? We've all heard this in your previous course. I talked about this a little bit in previous lectures. But these are slightly difficult concepts to get your head around. And hearing them multiple times really helps. So I encourage you, when you go on to your third year stats course and you encounter some of these concepts again, go back and reread the basic sort of readingfulness and reinforce these concepts. Because speaking from personal experience, it took many courses that I had to take before some of these things actually clicked. And that's just the truth of it. The main thing to remember about power and alpha and type 1 errors and type 2 errors is that you can only make a type 1 error in a universe where the null hypothesis is true. Right? You can only make a type 2 error in this other universe where the null hypothesis is false. Right? If the drug has no effect in truth, then that's the situation in which you can make a type 1 error. If the drug actually has an effect, that's the only situation in which you can make a type 2 error. Statistical power only makes sense as a concept in the universe where the drug has an effect, and you want to try to detect that effect. Power has no meaning in this other universe where there is no effect, because it's the probability of detecting an effect. If there isn't an effect, then there's no probability of detecting an effect. There isn't one. But the kicker is that we don't know which of these two universes we're in, right? We don't know as an experimenter. We're in one of them, and these different concepts apply in each of them. We don't know which one we're in. Alpha, the alpha level, is the singular concept that kind of straddles both of these universes. By adjusting alpha in the null hypothesis is true universe, we can control how many type 1 errors we make. If we take that same alpha level and we put it in the other universe where the drug has an effect, then our alpha level affects our power, affects our probability that we're going to detect the effect of the drug when it's there. And then we have these other levers we can pull, like sample size and effect size, to adjust our power. That's the concept that took me a while to understand, is that some of these concepts apply only in one universe and not the other. But we are actually only in one universe. We can't be in both at the same time. All right, enough of that. Let's move on and talk concretely now about follow-up tests. So I told you a couple of slides ago that if we make multiple comparisons after a significant omnibus test, then our type 1 error rate under the null hypothesis will actually be bigger than we think it is. It'll be our alpha level for each individual test, but taking those, let's say, 3 pairwise tests as a family, our overall probability of making a type 1 error is going to accumulate. It's not quite the number of tests times alpha. You might think if our alpha level for one test is 0.05, and we do 3 tests, maybe it's 0.05 times 3, which is 0.15. It's close to that. It's not quite that. The formula is this, and you don't have to remember that. You don't have to ever see it again. Oh, sorry, that's not the formula. That's the formula for the number of pairwise comparisons for k groups. So if we have k different groups, the number of possible pairwise comparisons is that. And just to illustrate how quickly that formula increases, if we have 3 groups, there's 3 possible pairwise tests. If we have 4 groups, there's 6 possible pairwise tests. Imagine a case where we had 10 groups in our ANOVA. There would be 45 possible pairwise tests we could do as a follow-up to a significant omnibus test. So that's a huge number of tests to figure out what's different from what. And in terms of the error rate, this is the formula that determines the probability of making a type 1 error in that family of follow-up tests. It's not quite alpha times C, the number of tests. It's 1 minus alpha to the power of C, and then 1 minus that. So we have 3 pairwise tests, then the type 1 error rate of that family of 3 tests is actually 14.3%. It's not 5%. The type 1 error rate accumulates. And just to take an extreme example, this is the number of pairwise tests that we do in our family of tests, and this is the type 1 error rate. If we do 13 pairwise comparisons, then our type 1 error rate is actually 50%. It's not 5% anymore. We're actually making a type 1 error half the time when the null hypothesis is true. So that's much higher than what we want. So the bottom line is we need some way of correcting for that accumulation of type 1 errors. Just conceptually, does anyone have a handle conceptually on why would the probability of making a type 1 error in a family of follow-up tests accumulate? Why would it be higher than 5% when the null hypothesis is true? Yeah. It's a bit hard, frankly, to think about concretely why it could happen. Yeah.
There's a probability of 5% for each test that we do.
That's right.
There's a 5% chance of making an error for each group. So if you're going to accumulate, say, 5% here, 5% here, 5% here, so just increasing the chance because you're multiplying those probabilities together.
Almost. It's not quite. It's this weird formula.
Right.
Yeah. That's really close. Yeah. I mean, in probability theory, the probability of one event and the probability of some other event and the probability of some other event, if the events are independent, then the probabilities don't accumulate, right? It's that gambler's fallacy, right? If I lose a bunch of times in Las Vegas, then the next time I must have a higher chance of winning because on average, right? If events are independent, then they won't accumulate. So if I'm saying they accumulate, it must mean that they're not independent. Yeah.
Because they're overlapping, so there's variability that you're like extra accounted for.
Yeah, exactly. There's 2 things, and that's one of them. Yeah, and that kind of relates to how I've answered your question as well. The tests that you do as a follow-up, they're not independent of each other. They're using parts of the same data. If I test placebo versus, I forgot the name of the drug, placebo versus drug 1, and then placebo versus drug 2, I'm using that placebo data twice. So those tests are not independent in that sense. The other concept is that imagine this was actually my data. And our omnibus test said, there's a difference. I don't know where. Now, when you look at the graph, where do you think the difference is? Which of those 3 groups do you think is different, most different? Or which drug do you think was sampled from a population whose mean was most different than the other populations? Yeah, that one, right? That one stands out as the one that's most different. So imagine you're only going to do 2 follow-up tests of the 3. I would do this one versus that, and this one versus that. That's the biggest difference. So, under the null hypothesis, that difference is false, right? That's leading us down a false avenue. That's just due to random sampling. And so if we choose our follow-up tests based upon the biggest differences that present themselves, what that means conceptually is we're chasing after the biggest random differences. And if we're always choosing the biggest of random differences to test, then we're more likely to be led astray. Right? If under the null hypothesis, sometimes we can get a small difference, sometimes we can get a big difference, and we always choose to test the big difference, then we're stacking the odds against us that we're making a type 1 error. We're much more likely to make a type 1 error and falsely declare that the differences are real if we only ever shoot for the biggest differences that present themselves. So that's the other concept that's involved. And just like we did simulations, incidentally, just like we did simulations for the null hypothesis here, where we simulated a situation where we're sampling under the null, you can rewrite that code, and instead of choosing mean equals 0 for all three groups, if you change those mean values, now you'd be simulating an alternate hypothesis, where the alternate hypothesis is true. Right? And you could calculate your power. Oops. I jumped over your phone.
Sorry, it's okay.
Oh, no.
Just leave it unplugged, it's fine.
You can follow up this significant ANOVA in simulations with follow-up tests, where you only test the biggest differences that present themselves from simulation to simulation. And if you then count out the number of type 1 errors you make, you'll find that it's more than 5%. All right, so that's the concept, is that type 1 error accumulates. And it accumulates pretty fast, so we need some way of correcting for it. If we chase the big differences, then our type 1 error rate is going to accumulate. Now, incidentally, what's the big deal? Why should we be concerned if our type 1 error is bigger than our alpha level? So it's 14% instead of 5. Who cares? What's the big deal? Like, what's the consequence? Yeah.
So the center is too liberal and would simply reject more hypotheses?
Yeah, we're sort of loosening our standard scientifically. And we're making it so that we're much more likely to falsely declare that there's a difference, that there's an effect, when there actually isn't. So we're much more likely to conclude things are different than each other when they're actually not. Which is not, I mean, it makes for a more exciting thesis if you can say there's a difference, right? But we want our scientific endeavors to be based on reality. If we're just storytelling, then yeah, we want big differences. Those are more exciting to talk about. They make for a better story. But if we actually want them to be a reflection of reality, we don't want to be doing experiments that are more likely to falsely declare that there's an effect when there isn't one. If you're, think of it this way, if you're a pharmaceutical company and you're testing the efficacy of various drugs to treat diseases, and your actual type 1 error rate is 15%, not 5%, you're going to end up approving all these drugs that you claim have an effect, that cost people or governments money, give people false hope, that actually don't. And you don't want to do that. So we don't, type 1 error rate seems like an abstract concept, but it has teeth. Okay, so how do we adjust them? So what I'm going to tell you about is a small selection of different flavors, essentially, of adjusting for type 1 error. The short answer is there's many, many ways, many different schemes people have come up with to adjust for type 1 error, to adjust for multiple comparisons. Here's sort of 3 standard-ish ones. One is called the Bonferroni method. I think that's the name of the person who invented it. I know Tukey is the name of a statistician. So there's the Bonferroni method, which is really easy to do. It's probably the easiest one to implement. You don't even need to have an R function to do it. But it's maybe a little too heavy a hammer. There's a second one called the Tukey method, which is perhaps the most flexible. It lets you test as many comparisons as you want. But again, maybe it's a little too heavy a hammer. And the Bonferroni-Holden method is kind of an adjustment. It's an adjustment of the Bonferroni method that makes it a little less severe. And I think of the 3, Bonferroni-Holden is the one that I most often will go to first. A lot of people just do Tukey because it's pretty standard and easy. And you might come across others. There's a whole variety of other flavors of adjustments. But let's look at these three. So the Bonferroni correction goes like this. Basically, you take your p-value, whatever it is, and you correct it. You correct it by multiplying it by the number of tests you do. So if you're doing an ANOVA on 3 groups and you have 3 follow-up pairwise tests, then you take the p-value for each of those tests and you multiply them by 3. And then you compare the corrected p-value to alpha. So if you get a p-value of 0.01 for one of those pairwise tests, and you're doing 3 tests in total, your corrected p-value would be 0.03. Good, it's still significant. If your p-value is 0.049, and you're doing 3 tests, then you multiply 0.049 by 3, and you get something way above 0.05, and it's no longer significant. So adjusting for type 1 error inflation could push a p-value from being significant to not significant. That's the way in which it corrects for type 1 error. If you're doing 10 follow-up tests, you multiply each p-value by 10, which essentially means you need a p-value of 0.005 to be significant at a 0.05 level. The other way Bonferroni adjustments are sometimes presented is not in terms of correcting the p-value and correcting and comparing it to alpha, but keeping the p-value the same and changing alpha. So if your alpha level is 0.05 and you've got 3 follow-up tests, you would divide alpha by 3. 0.05 divided by 3. That's what you would compare your uncorrected p-values to. So you might come across either way of presenting. So that's pretty simple. It's a pretty simple method. It turns out to be a little bit overly conservative when you're doing a large number of follow-up tests. Like I would say more than 5. Then you're over-correcting the type 1 error inflation. The goal of this, incidentally, is to push that type 1 error, the family-wise type 1 error, down back to alpha, whatever alpha is. In R, you can just feed the post hoc pairwise t function, p.adjust.method equals, and then tell it to do Bonferroni. And it will present you with Bonferroni adjusted p-values. So in this case, the p-values are all multiplied by 3, because there's 3 tests. Simple. So Bonferroni. The Tukey procedure, I won't show you the formula, because it's a weird, ugly, bizarre formula that does something bizarre and weird and ugly. It also adjusts the p-values. It gives you corrected p-values. And it allows you to perform all pairwise comparisons, no matter how many groups you have. So if you have 3 groups, it will allow you to do all 3 pairwise comparisons. If you've got 10 groups, it will allow you to do all 45 pairwise comparisons, and still have your family-wise alpha level at 0.05. It's less conservative than Bonferroni when you're doing a large number of tests. So if you're doing a large number of follow-up tests, Bonferroni is a bit too much of a correction, and 2p is more appropriate. In R, there's a function called 2phsd. HSD stands for honestly significant difference. You just give it your ANOVA object from the AOV command, and it will show you every pairwise comparison, the difference between groups, the lower and upper 95% confidence interval on that difference, and the adjusted p-value. So you would compare the adjusted p-value to your alpha level to determine the corrected version of your test. Okay, so that's all. I mean, the main things to remember is it allows you to test all pairwise comparisons. It's less conservative than Bonferroni when there's a large number of tests. So it's the one to use when you have a large number of tests. Basically, you can never go wrong. You just always use 2p tests. No one will ever criticize you. The Bonferroni home is a good general purpose correction, I would say. It's less conservative than Bonferroni, for sure, and we'll see how. directly related to Bonferroni. It's also less conservative than 2p for a moderate number of tests. If you're doing a truly gigantic number of tests, like 50 follow-up tests, then 2p is the way to go. If you're doing something in the medium range, like 5 to 10, then Bonferroni home is probably better than 2p because it's less conservative, but still good. And Bonferroni home is always less conservative than Bonferroni because Bonferroni home is just Bonferroni adjusted so that it's not as conservative, and we'll see how. What you basically do is you do all your pairwise tests and get your uncorrected p-values. You sort them. You sort those uncorrected p-values. And then you correct the p-values that are most significant the most. And then the next most significant p-value you correct a little bit less. And the next most significant p-value you correct a little bit less still, and so forth. So basically you step on the biggest differences first, the most. And you squash the less big differences a little bit less. So think about it, what I said before about type 1 error inflation relates to chasing the big differences. That's the spirit of a Bonferroni home correction, is it takes the biggest difference first, and it says that's the one I should correct the most. Because that's the one, if the null hypothesis is true, it's most likely to lead you astray. And then the next biggest difference, it corrects a little bit less. I don't have to correct that one as much, because it's not as big of a difference. So imagine you had the following 5 uncorrected p-values for 5 pairwise follow-up tests. You would first sort them from smallest to biggest. So that's the smallest p-value. That would reflect the biggest difference between groups. You would rank that 5 out of the 5. You would take that raw p-value and multiply it by its rank, and you would get the corrected p-value, 0.05. So that's the corrected p-value. The next biggest significant difference, so the next biggest p-value, you would multiply it by 4. So you correct it a little bit less, and you get 0.02. So that would be the corrected p-value. The next one, you would correct it a little bit less still, and you multiply it by 3, and you get that one. And you do that all the way down until the last one, you would multiply it by 1. You wouldn't change it. The smallest difference you wouldn't need to correct because it's the least likely to be the type 1 error. There's a little complication here, which the R function will do for you, but just so that you know what it's doing. The corrected p-values must always be in increasing order. The corrected p-values have to always, they're enforced to be smallest to biggest. But you can run into this situation like this, for example, where 0.019 times 3 is 0.057. The next biggest p-value, 0.022, which is bigger than that, it only gets multiplied by 2, and so its corrected value is 0.044, which is smaller than that one, in fact. Small, bigger, bigger, oops, that one's smaller. So instead of leaving it smaller, you just set it to equal that one. You just step it up to whatever the one before was. So you enforce that the corrected ones go from smallest to largest. So just be aware that that could happen. In case you're looking at raw p-values and you're looking at your home corrected values and you're like, huh? I thought you said that you just multiplied by the rank. When in the corrected p-values, they kind of go in the opposite direction. You just replace it with the next one. So the spirit of Bonferroni home then is the biggest differences, the most significant p-values are the ones under the null hypothesis that are most likely to be the type 1 error. They're the ones that are most likely to lead you to make a type 1 error. So they're the ones you should correct the most. Under the basic Bonferroni procedure, these would all be multiplied by 5. Right? Yeah.
But this has to just, because the difference between 1, 2, 2, 3, and 4, or 5 is the same, but the differences between the raw p-values are definitely not the same.
Yeah.
Wouldn't that, what if there's a very big variation in differences? What if that kind of screw it up?
a very big variation in the differences in the raw p-values.
Couldn't there be a test where we could account for those changes or like the differences?
Yeah, I think maybe. Remember what the distribution of p-values is under the null. It's a flat distribution, right? Every p-value is equally likely. So I think the way to think about it is, on average, these sort of differences are just going to average out in the wash. And the main spirit of this is that when you get an oops, when you get a really low p-value, that would ordinarily lead you to make the wrong decision on the null. That's the one you correct the most. Now the other thing you said is also true though, that the difference between 5 and 4 and 4 and 3 and 3 to 2 and 2 to 1 is the same, but the differences when you multiply these out can be different. And they can also be, those differences can also be different when you have a large number of tests, right? Here we go from 5 to 1. So the most corrected one is multiplied by 5, and the least corrected one is multiplied by 1. If we had 50 tests, then the most corrected one would be multiplied by 50, right, in order of magnitude more. And so the number of tests overall means that the correction factor you apply to the sort of smallest p-value depends on the number of tests. Which makes sense, because if the number of tests affects how much type 1 error accumulates, then of course you want to step on the lowest one most when you have the biggest accumulation. The mathematics of sort of how these things all relate to each other, whether they're linear or not and stuff, we're not going to get into. But just understand the spirit of it. That the spirit of the home part of Bond for Only Home is to correct the smallest p-values more. And in the post-hoc pairwise t-function, if you give the p-adjust method just the word home, then it will give you the Bond for Only Home adjusted p-values. So this has been good. You know, the concept of correcting for type 1 error, conceptually it's a little bit hard to grasp. Practically speaking, it's really easy. You just have to remember to give the p.adjust method something other than none, right? You'll see as you go on and you do your undergrad thesis or beyond that basically in all areas of science now, the standard is you have to adjust for type 1 error in some fashion. And if you try to send a paper to a journal or give a talk at a conference and you don't say how you did that, 100% someone will ask, hang on, but how did you adjust for type 1 error? And if you say, oh, I didn't, these are uncorrected, then everyone will, so you'll hear this collective groan from the audience, because it means we can't interpret any of this. We just have no idea what might be type 1 error and what might be a real difference. So it's a really important concept. Just very quickly, in your readings and as you go on, you might have come across what are called unbalanced designs in ANOVA. Unbalanced means you have unequal sample sizes in different groups. And that can be a problem for the ANOVA test. And you can think about why. It relates a bit to the homogeneity of variance assumption. My advice, frankly, is do your best to never have an unbalanced design. Because trying to correct for an unbalanced design is super ugly. There are various schemes and methods and calculations you can do to try to correct, but they're all ugly. There's a method of linear models called linear mixed effects models, which are a bit less sensitive to unbalanced designs, but that's a relatively advanced technique. So just try your best in your thesis not to have an unbalanced design. Sometimes you have no choice. If you're recruiting patients that are of a particular flavor and you're trying to control for age or something, it might be impossible to find one more person. If you have an animal study, mice could die, but try your best to have a balanced design. And I wanted to leave you with this little cartoon from XKCD that illustrates the type 1 error problem. Okay, so it won't take long. So someone claims jelly beans cause acne. And then their friend says, scientists investigate. But we're playing Minecraft. Okay, fine. So they do an experiment. We found no link between jelly beans and acne. P is greater than 0.05. So the friend says, hang on, I hear it's only a certain color of jelly bean that causes acne. Okay, fine, let's do more experiments. Okay, we found no link between purple jelly beans and acne. P is greater than 0.05. We found no link between brown jelly beans and acne. No link between pink jelly beans and acne. Nothing for blue, nothing for teal. Nothing for salmon, nothing for red, nothing for turquoise, magenta, yellow, gray, tan, cyan. Oh, we did find a link between green jelly beans and acne. P's less than 0.05. No link for mauve, or beige, or lilac, or black, or peach, or orange. Okay, so we did all those, how many is that? 20 experiments. What's the headline? Green jelly beans linked to acne. So what's the problem? Yeah.
Family-wise error rate.
Yeah, the family-wise error rate. So each of these individual experiments are based on the p-value having to be greater than 0.05. Now, there's two possibilities. Maybe green jelly beans do cause acne. Maybe they do. But maybe they don't. And that was just random sampling error, right? But that should be okay because our p-value was less than our alpha 0.05. Well, if you consider all these experiments as one family, then our family-wise error rate's actually way above 0.05. Right? Or think about it another way. This is 1 in 20 experiments. What's 1 divided by 20? It's 0.05. So that's our type 1 error rate. Right? That's kind of like doing our simulations from before. Right? We did 20 experiments under the null, and we set alpha to 0.05. What happened? 0.05% of the time we rejected the null. So either that's a type 1 error, because green jelly beans don't cause acne. That's consistent with that. But it also could be that green jelly beans do cause acne, and that is a correct rejection. And so, in my usual way, I'll leave you with the ultimate skeptics view, which is we just never know. We don't know what universe we're in. All we have is this framework for trying to interpret things. Okay. Thank you.